Okay, here we have a question from one of the slides in my astrophysics class talking about calculating the surface temperature or average surface temperature of a planet. The question on one of the slides was Mercury has an orbit with a semi-major axis A equal to 0.387 astronomical units, and eccentricity of E is equal to 0.206, which is the actual eccentricity of Mercury. Assuming that Mercury is approximately a black body, that's just going to change our equation slightly, even though it's not. It has a smooth surface distribution across the entire surface, or temperature distribution, so we're not going to go with any variations. What is the surface temperature of Mercury at its closest approach to the Sun, the perihelion? And what is Mercury's surface temperature when it is farthest from the Sun? Okay, well, let's first try to figure out what are these distances here. If this is Mercury right here, let's get a nice red. This is Mercury, and it's traveling in this direction. What is the closest approach? That would be when Mercury has reached this point. This mass right here is the Sun. This is the Sun right here. I guess I should make the Sun yellow. That makes more sense. Okay, this is our Sun. So what is this other little dot over here? What is this? This is Mercury's center of mass. So if you take the mass of the Sun and the mass of Mercury, which is on this ellipse, the center of mass, if Mercury is here, the balance between mass of all of them is at this point. So Mercury's center of mass. The Sun center of mass doesn't really move very much. It moves a tiny little bit. We're talking about a few meters. But Mercury's center of mass is way outside of its actual size and body. So it exists out here in a point in space in which that gravity is equalized. If you were between the Sun and Mercury, and you were at this point in space, you would not float towards the Sun, or you would not start being dragged in by Mercury's gravity. That's what that center of gravity is. Just like balancing a golf club on your finger. It's where the Sun is actually the head. Well, anyways, we got to get into this proof. It's kind of a long one. Okay, so we know from the earlier slides that we're looking at this. So the closest approach to the Sun from Mercury is this distance right here. So from here to here is the perihelion. And what is that? We got A. This is distance A. This is A. This distance is L. So if we take the distance A and subtract half of L from it, that should give us this distance here. So this distance, the distance, we'll call it peri, distance peri is equal to A minus 1/2 of L. By the way, eccentricity is defined as L over 2A. So this, you could put this A minus AE by rearranging this. Okay, and it gives us A and it gives us E. We could calculate L, or I could go ahead and do this formula, A minus AE. Since half of L over 2 is equal to AE. And that works out to be 0.307, and this is in astronomical units. Okay, that is our distance from Mercury's closest approach. Its furthest approach, right here. What is this distance? From the Sun all the way over here. This distance from here to here is the aphelion. Aphelion. And what does that equal? Well, we have A plus we have half of L. So either A, let's put this as distance, aphelion is equal to A plus L over 2. And L over 2 is the same thing as AE, so we can go A plus semi-major axis times the eccentricity. This works out to give us our distance for our aphelion is equal to 0.467 astronomical units. Okay, now that we know our distance, how in the world are we going to calculate the temperature on the surface of Mercury? This comes from the previous video, where it talks about the work or energy on the planet is equal to some function times the distance the planet is away times pi times the radius of the planet squared. So that's a little circle, and this is 1 minus the albedo. And what this term right here does is a perfect black body has an albedo of 0. In other words, it absorbs 100% of the energy. And an albedo, well, if a planet has an albedo of 1, this term goes to 0 and everything is reflected away. So it's perfectly white at all wavelengths. We also had that the luminosity of the planet is equal to 4 pi radius squared of the planet times Stephen Boltzmann's constant times the temperature of the planet to the 4th power. Well, this is just like Stephen Boltzmann's equation for the Sun, but you're just simply using it for planets. Okay, it says in equilibrium. In equilibrium, WP is equal to LP, work on the planet, and the luminosity of the planet. So what exactly is this work on the planet? This is the energy from the Sun to the planet's surface. Energy from Sun. From Sun to, this will be Mercury in this case. And this term, what is this guy? This is the energy released back into space. Ooh. Released back into, my spelling is getting bad, space. Okay, so that's what being in equilibrium means. So this planet isn't getting hotter, it's not getting colder, it's in equilibrium. So this will be a constant. Okay, looking at these two right here, we know we have this setup right here. So we have, let me switch back to my favorite color here. We have W, the work on the planet, is the force function from the distance of the Sun to the planet, times pi times radius of the planet squared, times 1 minus albedo. is equal to 4 pi times the radius of the planet squared, Stefan-Boltzmann's constant, times the temperature of the planet to the 4th power. Well, now we need to figure out what this term is. This term is defined as the luminosity of the sun. So how much work is being done on the planet has everything to do with the luminosity of the sun, or the star, I should say. It's the sun in this specific example, over 4 pi, the distance squared. So it's going to fall off. It's inversely proportional to the square distance of this little circle far, far away. Let me see if I can possibly draw a picture. I'm running out of time, so I'm going to skip that. So what is our luminosity then? We've got a lot of equations buried into this little thing. Luminosity, Stefan-Boltzmann's law, 4 pi, the radius of the sun squared, times the Stefan-Boltzmann constant, times the temperature of the sun to the 4th power. And what I'm going to do is I'm just going to plug this whole thing into here, and then I'm going to take this and plug all of this and plug it into here. And this is what we're going to get. Let's write all this out. We're going to get 4 pi radius of the sun, that's what this little symbol means, squared, times Stefan-Boltzmann's constant, times the temperature of the sun to the 4th power. All of that is over 4 pi times the distance away from the sun to the planet squared. That is this term right here. Now I got to add this part, times pi times the radius of the planet squared times 1 minus albedo is equal to, now we have the right hand side, 4 pi radius of the planet squared, Stefan-Boltzmann's constant again, the temperature of the planet to the 4th power. Now we can start canceling out stuff. There's too many calculations that I want to do here. Let's get rid of our 4 pi. 4 pi. We have the radius squared of the planet. Don't need that to figure out temperature. We have pi we can get rid of. What else do we have here? Stefan-Boltzmann constant. Don't need that guy either. Well, we've canceled everything out over here except for the temperature of the planet. Pretty cool, huh? We have the temperature of the planet to the 4th power is now equal to the radius of the sun squared times the temperature of the sun to the 4th power over 4 times the distance away from the planet squared. Okay, at this point, what I want to do is make this much, much, much simpler. We're going to try to calculate just this part right here. Now, remember we calculated the perihelion and aphelion of Mercury to the Sun. We did that in AU, so we're going to want this. We want to plug this AU into here. So that's going to have to. We're going to calculate the radius of the Sun in AU. And notice I went ahead and did away with this term. This term kind of disappeared because I'm assuming a black body, which is stated in the question. The question says black body. Mercury is approximately a black body, so it's reflecting a bit. So that means if it's a black body, A is equal to 1, A is equal to 0, and you just have this whole term multiplied by 1. So that's why this went to 1 and we ignored it. Okay, back to this. The radius of the sun is equal to 6.96 times 10 to the 8th meters. And we want to convert that to how many meters are in 1 AU? 1.49 times 10 to the 11th meters. That cancels our meters out and leaves us with the radius of the sun is equal to 0.00467 astronomical units. So now that we'll have astronomical units for our radius, that will be canceled by what we just calculated, our two different distances of Mercury, and leaving us with just our temperature. Okay, so now that I have R, I can calculate temperature of the planet to the 4th power is going to be equal to, let's go ahead and calculate this out. We've got the temperature of the sun at the surface is 5,800 degrees Kelvin. So if you take this radius, 0.00467, square it, you take this temperature, 5,800, and you 4th power over 4. That is what I'm trying to calculate right in this little bit here, and then we'll leave our distance squared in AU for the second part of the calculation. This is going to give us temperature of the planet to the 4th power is equal to, this will end up being 280 over the distance to the planet. Whoops, not to the 1/2. Not yet, anyway. Distance squared. Okay. This must be in some sort of units. Now let's take the 4th root of both sides, giving you the temperature of the planet, is equal to, I'm sorry, that's actually this to the 4th power. 280 is this term to the 1/4 power. So I have already performed this on here. If you have any questions, you're in my class, just ask me. Okay, so our 280 is where I already took the 4th root of all of this in here. This leaves us with 280 times distance. Let's bring it up here to the -1/2. Because with the 4th root that I have taken already, that gives you 1/2 here, and you bring it up. So our temperature of planet is equal to 280 times the distance. We have two calculations, our distance of our perihelion to the -1/2. And what was that distance again? Distance of the perihelion was 0.307. So 280 times 0.307 raised to the -1/2. That gives us our temperature of our planet, perihelion, is equal to 505 Kelvin. It's a little bit different than the slides answer, but there was a lot of different conversions and rounding going on here. And of course our temperature for the aphelion of our planet, the aphelion, is equal to 280 times, it was 0.460 to the 1/2. Temperature of our planet, the aphelion, turns out to be 412 Kelvin. And that is close to what the slides say.